Hi everyone. Today what we're going to work through, you can see the title up on the top, we're going to address remainder theorem. And in order to do that, I want to go through and deal with a little bit of division that we talked about last time. So, depending on whether you're using the handout or whether you're doing this work on like a blank piece of paper, you may have to copy out the table, or if you have the handout, you already have the table. What I'd like you to do is to complete that table doing a number of divisions. Now, all I want to do is I just want to kind of talk a little bit about the structure of the table. So, what it's telling you is to take this p of x, original function, and we're going to divide it 4 times. So, what you're going to do is you're going to take p of x and you're going to divide it first by x minus 3. Then you're going to divide it by x plus 2. You're going to divide the original p of x by that. So it's like we're resetting every single time. Then you're going to take p of x and divide it by x minus 1. And then finally, you're going to go through and take p of x and divide it by x plus 1. Don't mind my letters off on the side. I have trouble with the alphabet. Now, what we're going to do then is we're going to complete the chart. And so, I don't want you to be overly concerned about how we fill in the chart. What I want you to be concerned with right now is, can we work at a decent pace to do those divisions? So, based on what we talked about on last lesson, we should be good to be able to do some long division on a polynomial. And so, I'd like you to go through and take p of x and divide it by those 4 divisors. So, you're going to complete 4 divisions. I'm going to argue that I think you're working at a very good pace if you can tackle each one of those divisions in about 45 seconds. So I think if you can get to that point, then I would think that you're already working at a very efficient speed. So I'm going to say, let's pause the video, and roughly in real time, we should be back in about 3 minutes. Okay, give it a go, pause the video now. Okay, we're back. So hopefully we have those 4 divisions completed, and I just want to make sure that we're good on how we fill in the chart. Okay, so what you see on the screen now is how we would complete the chart. So hopefully when we went through and we did that division, everybody's solution matches up with the blue. That you can see that you got an answer of 2x squared plus 4x plus 9. And hopefully when you did that, you also found that you had a remainder of 30. That's going to give you some good feedback. Okay, did I get my first division correct? If we were working at a good pace, then I would feel pretty confident. I just want to talk now about how we fill in the chart. So you can see that middle column. We're going to present our quotients, comma, and then our remainder. We notice that up here because we're pretty good with that notation now. P of x divided by x minus b is what we're doing in that middle column. We're actually doing the division. So I want you to write quotient, comma, remainder. I want everybody to look at the first column that you have to fill in, that column that's labeled B. And if we can look back to the first column, you'll notice that all of our divisors take the form x minus b. And so, if my divisor was x minus b, and the actual divisor that I'm dealing with in this case is x minus 3, then my b value must be 3. And we could probably fill in that column pretty quick then. If my divisor was x plus 2, and all my divisors are x minus b, then my b value would have to be negative 2. Because now I would have x subtract a negative 2. That's why I see the plus. And so pretty quickly then we could recognize that that was a b value. That was our b value. And we're really starting to fill in that table. Okay. You have your 4 divisions. We should be able to fill in the rest of that table. And now that we've clarified a little bit on the b value, I want to focus in on that last column. So I'm just going to get rid of all my highlights here so we don't get too lost in all of them. And what I want to do is just focus in on that last column. We take a look up at the top and you have been asked to find P of B. And we are very good with our function notation, so we recognize that that's telling us to take our B value and sub it back into the function P wherever we see the variable. So if I'm going to deal with that on my first row, row A, then I need to find P of 3. And so I could make the substitution, 2 times 27 minus 2 times 9 minus 3 times 3. And just do that calculation and collect everything, and we should be good. So what I'm going to add to your plate now is I want you to go through and do the 4 substitutions. You now need to address P of -2, P of 1, and P of -1. If we can nail out those 4 substitutions, then we're going to come back and we're going to see how well we were doing at some calculation. Okay, so I want you to do those 4 substitutions. Pause the video now. Okay, we're back. So now we get an opportunity to check and see how our substitutions went. And so what you'll see then is you'll see our full table with all of our divisions. So we'll get a little confirmation as to how well our divisions went. And when we dealt with our substitutions, we should have found out that the first one worked out to be a 30. The second one worked out to be a -15. The third worked out to be a 0. And some of us are already seeing the pattern. And even if we hadn't done the substitution, we may have predicted that that last one would be 2. And so what I'd like us just to take a peek at, and I'm going to highlight, is what we have is this relationship that we can maybe see between our remainder and our substitution. And that's what we're going to get to the heart of as we talk about remainder theorem. So we've done a number of substitutions in this case. We've done 4. Through those 4, we were able to pattern out a little bit that, hey, I get the exact same remainder. So when I subbed in, my 3, I got the remainder as if I had divided by x minus 3. And we found that same pattern as we progressed. When you subbed in a -2, you got a value of -15. And that was the same thing as the remainder as if we had divided by x minus -2. And that's where we're getting with remainder theorem. Now, us walking through 4 substitutions and 4 divisions is clearly not enough for us to go through and prove a theorem, but it starts to give us the basis for something. So what we want to do is we want to jump in then and address this remainder theorem, because I am not exaggerating that I might argue to you that remainder theorem may be the most important tool that we use all year. So we really got to make sure that we understand remainder theorem to its fullest. And so what you see a little bit further down, right below your chart on your page, is we need to use the results of what we just found to make a conjecture. And we should be good that a conjecture is just another word for like a hypothesis. And so we need to make a statement then about the relationship between the remainder and the value of P and B. Now, I'm okay for us to get down something that's maybe a little less formal, but it tends to be a mixture between some notation and just some English language. That for us to be able to say that the value we got when we subbed B into P, so P of B, is the remainder. That was the remainder, the exact same value we got when we actually took P of x and we divided it by x minus B. Now, I'm just going to highlight for a second that aspect. That when I did the division of x minus B, I got the same remainder as when I subbed B, whatever my divisor was, x minus what, back into the original function. And again, as I said, we haven't done enough to prove it yet. But this does give us something to kind of work with. So let's try to take this and go a step further. So as you take a look at problem 3 on your page, we want to use that conjecture now to predict the remainder when we divide by those values. So if we're going to make the argument that we're working at a pretty good pace if we can do divisions in 45 seconds, then I would hope that if the question was simply asking you about your remainder, that you really don't want to go through a whole division process, because that's going to take 45 seconds if you're working at a good pace. That there is a better way. So if we use that conjecture then, and we know that our remainder is the same as if we did the substitution, then if I see that my divisor is x minus 1, then I know that I can find my remainder if I simply subbed in x equals 1. That will give me the same remainder as if I divided by x minus 1. And so for us to just do a quick substitution and say like there's your 1 plus your 2 minus your 7 minus your 2, there's negative 6. Super fast. That was like 10 seconds tops. That we now have a better way to go through and examine a remainder. So you guys take a look at B, and we should be really, really fast to work through B. If we are dividing by x plus 3, and all of our divisors take the form x minus something, then our B value, if you want to call it that, our substitution value would be negative 3. Because x minus the negative gives me my plus in between. And now I could do my substitution, and there's a negative 27. I have a 9 times a 2. I have a negative 7 times a negative 3. And if we clean that up, we've got 39 minus is a 12 and 10. There we go. Very fast. Now, again, doing 2 more definitely doesn't prove it. And since this is still so new to us, it's not like we really have confidence in that. We're just using 4 substitutions to make an estimated guess. Let's go through. We're going to deal with 2 more fast confirmations. What I want you to do is I actually want you to do the division now. So I want you to take x minus 1, and I want you to divide that back into your original. And I want you to do the same thing for problem B. Okay, we're going to go super fast. You've got a minute and a half. That's 45 seconds per division. And we'll see if we get down to the same thing. Okay, so let's pause the video now. Okay, we're back. So now let's just get a little confirmation. And so hopefully you were able to go through pretty quickly. And the whole point of doing those 2 divisions was to get a little extra division practice to see if we're working at the right pace. But more importantly, if I was to highlight, you found that you got a remainder of negative 6, and we got a little confirmation that we can find that through substitution. You got a little remainder of 10, and we could find that through substitution. So that's built us up to like 6 problems now. It's still not enough to be able to claim that this is always the case. In order for us to use this theorem, we need to be able to prove this theorem. So we're about to move into a proof. The last part I want to knock out is what you have on your page is question 4. And this problem is one that I want you to just take like a second. I mentioned it on division. You take a second to just go like, okay, is something a factor or is something not a factor? So to hit up that question again, when a divisor is a factor of a polynomial, what is the remainder? And hopefully we got a nice big 0 on there and we're good. Let's keep that idea at the forefront of everything we're doing. Okay, let's jump in now and prove this as a theorem to make sure that we can use it. Now, what you see on the screen is just a little heading. We're going to get this down in our notes. So this is not going to be on that handout page that you have. We're going to work our way through a remainder theorem proof. I'm going to argue to you that this may end up being one of the easiest proofs you will address all year. I'm going to argue to you that the idea of proof is probably still very difficult. Like, you probably are in this course because you are very, very good at following instructions. In past math classes, if we had asked you to solve something, you're pretty good at solving an equation. If we ask you to simplify, you're really good at expanding brackets, collecting like terms. That when we give you an instruction, you've built up the skills to be able to do that. Proof, on the other hand, is this wide open statement that just says, hey, show me that something's true. And without that initial instruction, it can be difficult to walk your way through. Really, your only level of proof to a significant degree is maybe doing some trig identities in grade 11. That idea of making left side look like right side to try to show that something was always the case. What we're going to do this year is we're going to continue to work on your skill level and your strategies to be able to prove things. So let's start off with this one, and I'm going to give you a hand to get you going. We started off with an expression that allows us to represent any polynomial that includes a division operation. And so since remainder theorem is talking about when we divide by something, then this is the remainder, and so on, then what we want to do is we want to start off with a form of an expression that includes division, that includes remainder. And so we have that expression then that we introduced when we were dealing with our polynomials. So P of x is equal to D of x times Q of x plus R of x. We should all be comfortable with that statement now. Okay, so how about we use something that incorporates some of those features that we're trying to prove? We are trying to prove that when we take any polynomial and we divide it by that linear divisor, by x minus something, that we get a remainder that would be the exact same value as if we had just subbed in whatever that something was. So, how about we work our way to put the details into that green line? That green line is extremely general. Notice there is no statement about what P of x looks like, nor D, Q, or R of x. However, when you look back in the remainder theorem, you notice that there were some specifics. The specific was really that your divisor was always in the form x minus b. So I can put that in for D. Now, was there any specific about the Q of x? No. Now, we may have always got something that looks similar, but I'm hoping that we get why we did. That is, when we look at Q of x, we may have been tempted to say, yeah, but Q of x was always like a degree 2 something. It was always quadratic. And I'm going to argue to you that it was always quadratic because your original was always cubic. And so it should make sense that if we were to take a linear expression times a quadratic expression, we would get a cubic expression. However, we want to deal with remainder theorem for any type of polynomial. And so although in our chart, we ended up looking and we said, oh, but look, it was a cubic, that doesn't mean that it's always going to be a cubic. We want P of x to be quadratic, we want it to be quartic, we want it to be any degree. So we don't have anything specific then that we could throw in for P of x, and that means that we have nothing specific for Q of x. However, we do have something specific for R of x. You had a problem in your practice that asked you about that division process. And I'm hoping that through some patterning and some logic that we can maybe see the relationship between our divisor and our remainder. There was a specific problem that asked you, if your divisor takes a certain form, then what are your options for your remainder? And I'm hoping that we realize that our remainder always has to be 1 degree less than the divisor. At least. So, like if my divisor was quadratic, then my remainder could be linear, or it could be a constant. But it had to be a degree less, at least, or else I could have taken out more. We could have divided more. And so when we look back at our red line, if my divisor is linear, then the only degree that remains for my remainder would have to be a constant. And so if it's a constant, then it's not really a function of x. And so I don't have to write it as r of x, I can just write it as r. Okay, that is a great first line in terms of our proof. We like that. Okay, I'm just going to get rid of my yellow or gold chicken scratch, because now we can put in some details about our remainder theorem. Remainder theorem was stating that P of B is equal to the remainder as if we divided by x minus b. Well, let's put in some of those specifics. We're talking about P of B. And so in my function notation, if I replace one of my x's with a b, then I need to replace all of my x's with a b. And you guys should be one line away from proving remainder theorem. My left side is P of B. Well, on my right side, b minus b is going to become 0. 0 times anything is 0. And we are left with r. And there we go. There is our proof. What did remainder theorem say? It said when I sub b back into my original, it's going to give me my remainder when I divide by x minus b, and you can see that proof on your screen now. Nice. So now that we've proven it, we get to use it. But before we get into using it, I'd like to get down a more formal statement for what remainder theorem looks like. So in your notes, I think you want to jot this down, because that is a formal statement in blue for what remainder theorem is. When a polynomial p of x is divided by x minus b, then the remainder is p of b. There's your statement. However, I want us to walk through what we found as an extension and what we can see in red. Red's going to state when p of x is divided by ax minus b, the remainder is p of b over a. So this is going to be a little bit of an extension from what we did in our practice. So in that chart that we went through and completed at the beginning of today, I actually put in something that was a little more specific. When I had said that all of our divisors were linear, that actually wasn't as detailed as what it really was. That all of our divisors take the form x minus b. But notice, I actually fixed that the coefficient on your x had to be 1. Well, what we're going to do is we're going to pull that restriction off. And we're going to extend that to a generic linear divisor, which means we have no restriction on what the coefficient could be in front of your x. Now, how do most people tend to remember this? Over time, I've noticed that maybe a good way to think about this, as you're trying to come up with what is your substitution into P, is that quite often I have students who kind of think of it as like solving x minus b equaling 0. That after we just did that proof and we saw that when we subbed in b, Then we ended up getting a b minus b, which gave us 0 as our divisor, which then multiplied by our quotient wiped everything. That really it became like, well, can I solve for my divisor being equal to 0? And that's how I can find my substitution value. Well, the same thing would be true here. That really what we're looking at is my divisor of ax minus b, I want that to equal 0. And so when I isolate for x, then I can see that, oh, so now I just have to sub a fraction back into p. And what is that fraction? Well, it's b over a. Like in most cases, it's not like you solve that. You can just visualize isolating your b, dividing out your a. So there is an extension for us. I don't think we need to demonstrate that to walk our way through. I think we can make the connection in the ideas we have. So I just want to hop back to the chart for a second. And in that chart, we had that substitution and that completion. If I was to just like slide in like a question F, and I was to say that, well, what if my divisor was 5x plus 7? Like something like that. That we should be good, that what I would then calculate over here in my P of B is I would need to find the value of negative 7/5 being substituted back in. To get my B value, I would now have to get rid of my 7, divide out my 5. And so if I was to put in a little question G and say like happy face X plus star, then I'm hoping that we could pretty quickly say that, well, I would need to sub in negative star over happy face. Just something to keep in mind as we go. We're going to need to have that as we progress. Okay, now that we've proven it, now that we've stated it, now that we've extended it, now it's time to jump in and start using it. So on your page, the back of your page, I've got a number of examples that I want to walk through today. Some of those examples are going to be just merely for communication. That is, how do we properly express the idea that we're trying to deal with? And then some other ones are basically just how do we use remainder theorem? How do we use it as a tool to enable us to be a little more efficient with things and in some cases do some things that maybe otherwise we couldn't? Okay, let's jump into some of those examples. Okay, so question 1, you guys notice, I could have asked you question 1 last day to determine the remainder when we're taking that p of x and we're dividing it by x plus 2. That we could have gone through the whole process of doing some long division, but now that we have remainder theorem in our back pocket, we should be pretty good then. That to be able to come up with that remainder, really all I need is p of negative 2. If all my divisors take the form x minus b, then if I'm dividing by x plus 2, then my b value would be negative 2. I'm going to sub that back into my original. Well, the rest just becomes about calculation then. Like 2 times, that's going to be a negative 8. Some people like to put in this line. I don't think it's necessarily a bad line. That when you have powers, just evaluate each power. It's going to help with some sign mistakes and maybe some calculations. And that's going to give us a negative 32 minus 12. I think we get to negative 44. And there we go. So real quick for us to be able to work our way through using remainder theorem. Nice. Okay, let's keep it going. You take a look at problem 2. Determine the remainder when that is divided by that. And so I think we should be okay to tackle this one. So if you're feeling really confident, then I want you to pause the video and jump in and solve the problem. But what I just want to do before you do that is to talk a little bit about form. I want you to notice when the differences between problem 1 and problem 2. Notice in problem 1, I called your expression a function. We've labeled it with function notation. And notice in problem 2, we didn't. I want you to imagine that this was your test question. It was already pre-printed out on a page ready for you to complete. Well, you would have to either go sub x equals back into 2x cubed plus 3x, of which we don't want to take the time to write all that out. But instead, if we can just like sneak in like a little f of x equals, like seriously, sneak it in at the beginning or the end of your expression, you've now called that a certain name. The same way as back in grade 10 and 11, if you had a system of equations, you would label them as equation 1 and equation 2. Same thing here. Let's sneak that name right up into the problem, because now you can say that what you're looking for is f of negative 5 halves. Now you don't have to write out a big substitution statement. You can use the name of the function and function notation to cut down on some of that communication. Okay, now I want everybody to go through, make the substitution of negative 5 halves, and let's see how well we work with making a substitution of fractions in there. Okay, so everybody's going to give it a shot on their own. Go ahead and pause it now. Okay, we're back. So in this case, for us to work through, this is one of those ones where I think it's a pretty good thing for us to make the substitution. I don't think you want to necessarily waste your time blindly just writing in a negative 5 halves wherever you see your variable. However, for us to go through, I think that's a pretty good first line. Now you've made the substitution in and you've evaluated each individual power. Because now your next line is to go and say, okay, I'm going to need a common denominator. And this is where it's going to help us to find the lowest common denominator right away. I'm hoping that you did not get a common denominator of eighths. And I'm hoping that we had a common denominator of 4. Because we saw in the first term, this 2 will cross-reduce with that 8. So I can reduce that first fraction. Notice for anybody who multiplied the 2 in and got negative 250 eighths, that fraction would reduce to negative 125 fourths. And you can see it in blue. So that's going to make my work a little bit easier because at least I've reduced. If you had it in eighths, then for certain we're going to have to reduce our final answer. Maybe now I was able to avoid that. On top of, now I get to work with smaller numbers. So now I don't even need a common denominator in the second term. Multiply my 3 in, I already got fourths. My third term, this negative 7 times negative 5 halves, my negative times a negative is going to give me a positive. Oops. And when I multiply that in, I'm going to get 35 halves. Now I need to change that to a denominator of fourths, so I'm going to double that to a 70 fourths. And now with my 3 on the end, that's the easiest one to change into fourths, 12. Okay, I can go ahead and put all that stuff together. I'm going to get a negative 50, 20, and an 8 fourths, which I can reduce down to 2. Nice. So hopefully our approach was somewhat similar, but maybe in terms of that approach of going down to try to simplify with fractions, you may have found something useful in my strategy of how to reduce and how to be able to work with some smaller numbers. Okay, we've done 2 substitutions using remainder theorem. Now I want to jump into some stuff where like maybe we can actually apply it to some situations. Let's take a look at the next example. In problem 3, pause it if you want to give it a read. When we're going to take that cubic and we divide it by x minus 3, the remainder is 12. And the problem asks me to find the value of k. So I have to find the value of k. And maybe if I read that problem really fast, I didn't even notice that there was a k in there. There's my k. And actually, I shouldn't even really highlight as much that I just highlighted. There's my k. So I want to walk through this problem, but I want to give you an opportunity to try to solve it. So I want everybody right now to take a couple minutes and play around regardless of comfort level to try to find the value of k. Okay, pause it now. Okay, we're back. So I'm going to deal with this problem maybe about as ugly as you could. So I am hoping that no one has this on their page. And I'm going to argue to you that actually if you do have this on your page, you're being stubborn for today. That is, we really haven't acquired the theory that we needed to for today. And I'm telling you that you're actually missing something then. So let's imagine that I had no clue about remainder theorem. That's what I mean when I say I'm stubborn on today. Nope, haven't picked it up yet. Then I'm holding on to long division. And maybe what I'm doing then is I'm going to go through and I'm going to say, okay, I'm going to take x minus 3 and I'm going to divide that into x cubed. Okay, so now I start the division process. What would I multiply x by to get me up to x cubed? X squared. Why? Because I get this. Now I find the difference. Okay, well, when I find that difference, and I'm just going to hop over onto the side, I need to take a negative kx squared and subtract a negative 3x squared. Okay, I am hoping that most of us could at the very least see that that is that. Now, I hope that we see that because we just looked and we said we collected our coefficients. I'm okay if we looked at that and we thought about like, well, we common factored out an x squared. I'm okay with that, but I don't think that that's your best reasoning. Like, I want you to notice that what I did in green is actually what you've done since the day you learned how to collect like terms. If I asked you, what's 5a plus 3a? Probably at some point in your life, that was referred to as like 5 apples plus 3 apples. That when you actually put 5a plus 3a together, you say that you have 5 plus 3 of those a's. And you learned how to collect those terms well before you learned how to common factor. That really all we're doing is we're just putting together our coefficients of those variables. And so if you look back up at the green, if I have negative k of something plus 3 of something, then I have negative k plus 3 of that something. Now, if we take a look inside those brackets, that's just kind of a bad form because I have my negative value first. And so I should then write it in this form because now I get to write less operations. Okay, that was us subtracting. So now I've got my 3 minus k x squareds. Okay, I'm going to get rid of all that green on the side. You can rewind it if you wanted that on the side. And now I'm going to bring down my 17x. Because now I'm going to repeat the whole process over again. Okay, so now I'm going to ask myself, well, what would I multiply x by that gets me up to a 3 minus kx squared? Well, I would have to multiply it by a 3 minus k and another x. Okay, so if I multiply that out, then I'm going to get my 3 minus k x squareds minus 3 times 3 minus k x's. Okay, this is starting to get ugly. So what I have on that next line then, unsimplified would at least be this. 17 plus 3 times 3 minus k x's. Remember, it turned into a plus because I'm subtracting a negative. Which then meant that I could clean that up on the inside. And I would notice that I would have 17 plus 9, so there is a 26 minus 3k x's. And now I could go through the same, what would I multiply that by? Oh, bring down the plus 6, and then what would I multiply that by? A 26 minus 3k, and now I can okay, I'm even just going to stop there because I'm hoping that you guys are looking at that screen and you're going, oh my goodness, this is getting ugly. But I just want you to picture the process. Could we see taking that value and multiplying it back in? This will cancel out. We'll have some other expression down here that's going to have constants and k's in it, of which we will be able to find the difference, and that difference is going to have constants and k's. Okay, well, now let's go back to the problem. It tells you that that remainder equals 12, so we could set that equal to 12, and we could solve that equation. Okay, can we see the process? I'm hoping. I'm hoping we're also looking at that going, I never want to follow that process again. And this is where I say that we are not opening up to the idea of remainder theorem, and we're being stubborn if we're holding on to division. Instead, I'm hoping that we just said, like, well, I'm dividing by x minus 3, so I get a remainder of 12. Well, I have remainder theorem in my back pocket. And so if I just snuck in like a little f of x equals, then if I'm dividing by x minus 3, I could just substitute 3 in, and I know that I would get 12. So why don't I sub 3 back into f? Okay, 3 cubed minus 3 squared is 9, so times k, plus 17 times 3 is 51. And you now have a grade 9 equation that you can solve. Okay, maybe we spend a line just cleaning up the left side. That's a 7884. Now that means we have a negative 9k equals a negative 72, and k equals 8. I'm going to bet that everybody wants to work through the blue as opposed to that big, long division process. Just look at all your risk for mistake of what you have in that long division process. But I'm hoping that we can kind of examine that and we can see how we would have got down there. Like maybe even we can tie some stuff together now and realize that this remainder should have been that. Okay, I'm hoping that that problem motivates you enough to say, I want remainder theorem to be a skill that I have. I want that to be a piece of theory that I am able to apply. Okay, let's take a look at the last problem. I'm going to ask you to pause the video here and give that problem a read, okay? Pause it. Okay, we're back. So we've had a chance to read it, and I'm hoping that we don't find this problem too daunting. You look at it and you say, well, this is very similar to problem 3. The only difference is you've thrown 2 unknowns in the problem. But that shouldn't be that big of an issue because you have this division process with a remainder, and you then have this divisor with a remainder, that if you're looking for 2 unknowns, I've given you 2 situations, we should be good. So I'm not even going to leave you with this one like I think we should, but the whole reason I'm actually talking about problem 4 is just to make sure that you are following proper form when we solve a system. Okay, we have reviewed how to solve a system this year. This is the last time I'm going to walk through. After this, I just assume that we are all following perfect form when solving a system. So I'm going to deal with the blue information first. My expression is called p of x, so I can use my function notation. I know that p of 2 has to give me negative 3. And because of that, then I can sub in. So I know that 3 times 8 plus 4c plus 2d minus 7 has to equal negative 3. There is me subbing a 2 in everywhere I see an x, setting it equal to negative 3. Well, I can clean that up pretty quick. I know that 4c plus 2d, well, my 3 times 8 is 24. Subtract off your 7. There's a 17. To get rid of a plus 17, I need a minus 17. And I'm hoping that we take a look at that equation and we maybe say, hey, everything has a common factor of 2. Yikes. Let's shrink it down. So let's reduce it and divide out that common factor. Okay, I could go ahead now and do everything I did in purple. If I see I'm dividing by x plus 1, then I can sub in my negative 1, and that's going to equal negative 18. And now I can do everything my function notation says. Replace all my x's with 1. Well, that's a little easier to work through. Because I'm subbing in the negative, I just got to really be conscious of my signs. And so I get c minus d. To get rid of a negative 10, I need to add 10. And there we go. So notice we have 2 equations, both with the same 2 variables. You guys should be able to solve that system. That's grade 10 work. So, proper form, make sure that we label each of those equations and we circle those. There is your universal notation for an equation. You don't need to write them above each other. We should be good to take a look at this right now, and I would hope that for most of us we would use elimination because you notice that your coefficients on your d are the same. And so if I took equation 1 and I added it to equation 2, then I'm going to eliminate my d's. 2c plus c is a 3c. A positive d plus a negative d wipes them out. Beautiful. Negative 10 plus negative 8, negative 18, and I can solve that equation quickly. Now that I have c, I'm going to sub my c equals negative 6 back into one of my originals, probably equation 2. The numbers are smaller. That means I have a negative 6 minus 8 equals negative 8. I have no idea why I just wrote that down. How about minus d equals negative 8? And so I end up getting a d value of 2. Now, if this had have just been a system, actually it does. It doesn't ask me for what is p of x. It just asks me for what are the values of c. Nice. That means I write down my values as coordinates in alphabetical order, and we're good. Okay, problem 4, I'm hoping wasn't very difficult. I wanted to use that one as an extension of problem 3, but also a last opportunity to talk about the necessary form in your systems. Okay, there's remainder theorem for us, and we want to make sure that we have that theory and the ability to apply it in a very comfortable way. We're going to be using it so often. I was not exaggerating when I said this may be the most important piece of theory we use all year. Okay, your job, jump in and get some practice. Okay, good luck.